As per Hydraulic Institute standard, NPSH is the liquid energy, above the vapor pressure, at pump inlet. Let's simplify this statement. Each pump requires some minimum absolute pressure at pump inlet to avoid cavitation. This minimum absolute pressure, or absolute head in terms of height of liquid column, at pump inlet is known as net positive suction head. If we draw the pressure profile across the pump, it will look like this. Here, this line represents the pressure profile across the pump. As you can see, pressure is continuously decreasing as the fluid approaches the pump inlet. And the pressure drops to minimum value at point B, which is located at the impeller eye. The pressure starts to increase as fluid approaches pump outlet and reaches a maximum value at pump outlet nozzle. The net gain in the pressure between point A and C is known as total developed head. This straight line shows the vapor pressure corresponding to the fluid temperature. If the pressure at pump inlet drops below vapor pressure, the fluid will evaporate and generates small vapor bubbles. These bubbles carried along with the fluid and collapse instantly when they get into areas of higher pressure. This will result into excessive noise and vibration due to collapse of vapor bubbles. Also, it will damage the pump impeller and casing due to erosion. This whole phenomenon is known as cavitation. This minimum absolute pressure at the pump inlet, which is above the vapor pressure, represents the net positive suction head available. Now, I will explain how to calculate net positive suction head available at the pump inlet. Suppose we have a pump which is taking suction from water tank 1 and supplying water to tank number 2. This line represents the reference datum, as you can see here. The reference datum line is passing through center line of impeller shaft. You can refer this sketch for reference datum, which is given in Hydraulic Institute standard. The water in the tank 1 is filled up to height H from the reference datum. The pressure at pump inlet, due to water column height H, can be written as water density, ρ, times gravitational acceleration g, times height H of water. Units of pressure is Newton per meter square. However, it can also be written in terms of height H of water column. The unit of this pressure head is meters. In addition to this pressure head H, the atmospheric pressure also acts on the free surface of the water, which can also be written in terms of height of water column. That is, atmospheric pressure divided by water density ρ and gravitational acceleration g. Since the water is flowing with average velocity v through this inlet pipe, it will have some kinetic energy. This kinetic energy can be represented in terms of velocity head as v square divided by 2g. As you can see in this figure, I have shown atmospheric pressure head, static head due to water column H, and velocity head. If we add all these terms, we will get the absolute head at pump inlet. To avoid cavitation, this absolute head at pump inlet must be greater than vapor pressure. So, if we subtract vapor pressure from this absolute inlet head, it must be always a positive term, and known as net positive suction head available. Till now, we have understood what is net positive suction head available. But how much net positive suction head is required can be calculated by testing a pump. The most common method, often known as constant flow method, is used to determine the NPSH. In this method, the pump discharge valve is kept at fixed open position, so that pump flow remains constant. However, the pump suction valve is throttled. Due to throttling of suction valve, frictional losses in the suction pipe increases. And because of this increase in frictional losses, net positive suction head available at pump inlet reduces. However, pump developed head and flow remains constant until a point where net positive suction head available reduces below vapor pressure. After each throttling of suction valve, pump manufacturer notes down the total head developed by the pump, and net positive suction head available. The pump manufacturer repeats this step, until a point where the total developed head decreases by at least 3%. Then, a graph is plotted between total developed head and net positive suction head available. This graph will look like this. The point A, marked on this graph, where the total developed head reduced by 3%. The net positive suction head available corresponding to this point A, is known as net positive suction head required. It is also known as NPSH. The ratio of net positive suction head available, and the net positive suction head required is known as NPSH margin ratio. This ratio normally lies between 1.1 to 1.5. As you can see here, NPSH margin ratio depends on multiple parameters like type of pump and its application.